Hi again, and welcome to another lecture on linear regression. This time I'm going to demonstrate how to perform multiple linear regression statistical tests using Python Jupyter Notebook. To start, multiple linear regression refers to a statistical technique that's used to predict the outcome of a variable based on the value of two or more variables. So it's sometimes also known as simply as multiple regression or multiple linear regression, but it's an extension of linear regressions. I covered the simple linear regression in a previous video where the continuous variable that are in play or bivariate. In other words, there are two variables. We are looking at the effect of the independent variable on the dependent variable. However, with the multiple regression, the variables that we want to predict, which is also known as dependent variable, actually is looked at through the values of multiple independent or explanatory variables. So if we were to, in simple linear regression, if we were to analyze the effect of one independent variable of, let's say, GDP over emission, then in a multiple linear regression, then we are looking at least two or more explanatory variables or effects of independent variables on the dependent variable. So, as you know, multiple linear regression overall regressions could take multiple linear regressions could take two forms. There's the linear regression, there's the nonlinear regression. Again, it's a statistical technique that uses two or more independent variables. It's very important to understand that it's the most basic principle of multiple linear regression. And then the technique enables the research analyst to determine also the variation of a model and the relative contribution of each independent variable and the total variance in the model. So to start, it's important to understand that before we conduct any before we conduct any type of analysis or any type of statistical analysis or model, it's important that we should follow and ensure that all of the assumptions for that specific model is met. So for the linear regressions, please refer to my video where I've talked in details about those assumptions that need to be met before we even pull our sleeves to to engage in the actual analysis. But just in a nutshell, it's important that uh, there is a linear relationship between both independent variables and dependent variable. That's the most important assumption. And second assumption is that make sure that the data that you're looking at, the variables are normally distributed, that there are no anomalies, and the variables are not highly also the autocorrelation is that make sure that the independent variables are not highly correlated, or because when you have multicollinearity, then you're actually looking at independent variables. Actually, that's a problem because it's difficult to figure out the specific variable that contributes to the variance in the dependent variable because you're pretty much looking at the same independent variable. And make sure that that takes care of the autocorrelation part. And then I said linearity, endogeneity, normality, autocorrelation, multicollinearity. So these are the five most important assumptions that need to be met for you to even start to look at the possible analysis of variables for through the linear regression model. So let me start with a Jupyter Notebook here. I'm going to use a Jupyter Notebook for all of my Python demo videos because it's easier. I had between VS Code and Jupyter Notebook and PyCharm, I had to select this. I have experience with it. It's also much friendlier IDE than a lot of other IDEs that are available out there. The data set that I use for the sake of this practice is the same data set from the simple linear regression, which is the countries of the world and their economic indicators, and also environmental indicators, and where those countries are in terms of the indices for those indicators. So before we even start to bring the data set onto Python, it's important that you do some initial configuration to make sure that your notebook or your tool knows where to fetch the data, parse or import the data from, and what directory to communicate with your data from. So first thing first, let's go ahead and make sure that we assign the path or the directory where we will be importing this specific data set from, which is where I stored it. So assigning work destination or destination. So in that case, you need to download and activate the OS module. So the OS module is very important for you to be able to assign work destination or even look at what the work destination looks like. So um, assign work destination. Then you can say start with the OS library. Right, make sure that you import this library, and there you go, it's now imported. And then you can start with OS CHDIR, and the that's actually uh, the the uh, the command to tell Python to designate your directory for this specific path. And so in that case, I'm going to put my path as C, and then make sure to use uh, slash backslash users, and then it will be public. That's where I've stored my data set on. Yes, I forgot. It's actually not backslash, it's slash. Uh, there you go. Your work destination is now being assigned. Next thing you're going to do is you're going to check. Let me just put a note here. And then check. And then let's go ahead and check it to make sure that this is actually where this is where actually the destination, to see where the destination is assigned. Oops, I get width is in R, get CWD is get WD is in R, so get CWD is in Python, and you also have to use the name of the library as a prefix. So sometimes I mix up between Python and R. The syntax are quasi similar, so bear with me. All right, so this is the destination that we have based on what we assigned earlier. So now that we know where Python, or now that we assigned Python or told Python where to fetch our data set, now we're going to go ahead and do a fetch. So that will be, the name of our data frame will be data, and then we're going to use, before anything else, make sure that you have all of the libraries and packages that are needed for the sake of for you to be able to do analysis, all of them available here. So the most important one, pandas, numpy, uh, seaborn, sorry, um, matplotlib, mp maybe. All right, so let me just make a note here that you need to assign all of these. Sorry. Install and activate needed packages for your analysis. All right, so we need the pandas One of the most common libraries that use in data analytics and science, NumPy for numbers and statistic models, Seaborn, more like Seaborn Matplotlib, or more like for graphic visualizations. And I think the last thing that I need is stats models, and that will be SM. All right, so let's go ahead and oh, I forgot to put IPR plot here. All right, let's go ahead and run this and wait for the start. There you go. So all of those libraries now been activated and brought onto our environment. All right, so now that we have those libraries activated, let's go ahead and use the pandas library to bring our CSV file onto our browser, onto our Python environment. There you go. So the file that I would like to import is called country profile.csv. So let's go ahead and click on run. And I'll just go ahead and check to make sure it's been imported over. There you go. They're all here. Um, the descriptive or exploration of the data set in terms of uh, you know, to see what the the data set looks like, the pattern and distributions, and also to check for those assumptions that I talked about at the beginning of the video. You will need to do a series of data preps and exploration and scatter plots, that kind of stuff. That is a whole different course of action that you need to do. But in this case, the variables that I will be using for the sake of this analysis, they are tested for their normality, autocorrelation, multicollinearity, and also for the independent dependent variable. So I have done those, but the good practice is for you to actually, uh, you know, put your data in terms of graphs and look for anomalies as part of this whole assumption testing. So um, there you go. One of the most basic things you can do is to actually look at the description or descriptive statistics of each of your variables. Which is the count, and the mean, which is the average. Uh, excuse me. The average, the count, which is the count of rows of records. The mean is the average. Standard deviation, which is the distance, standardized distance difference from the mean. That's a whole different thing that I may have I may have talked about in other videos. So I'll probably have a special video about this. Minimum is like the least number distribution, the smallest number, and then 25th percentile is the first quarter, 50th percentile is the second quarter, the middle of this distribution, 75th percentile is the third quarter, and maximum is the highest number in our distribution. So some of these statistics actually can, tell you what your data really looks like from a high level details. At least, if you're looking at, let's say, if one of your variables is age, and then you see an average of, let's say, 78, and then you see the maximum 347. So that could not be practical, feasible, or possible. So therefore, that could be an error. That could be, again, something that you have an outlier, this extreme outlier that you need to fix before you even start to perform your analysis or further or move further in the data analysis process. You can also do data head, just another maintain function. These are methods. Uh, Sometimes I use the word command, function, methods interchangeably, but when it comes to the actual semantics of Python or each one of the placeholders, the functions, the functionalities have different acronyms and terminology that are used. So you probably hear me call this a command, which is a general term for, but which is a general term for what we tell Python to do in a script. But in detail, this is actually a method type of command. So So a method command that you can run is the head end. So if you don't want to look at everything, you can look at the first five records or rows, and again, Python or any data science tools are not meant for us to actually go and look at each of the records or rows. That's not practical. That's not the job of data scientists, data analysts. Um, this is why there are automated techniques and practices that you need to apply to be able to find anomalies without having to do manual review of your data set. So that's why don't be surprised if you don't see all of your thousands of records on a basic view. So now that we have looked at everything here, and we're going to create we're going to run our model. But before we do that, there's something that I always do, especially when I have multiple variables. Uh, I, I I I I think it's really good to do, especially if you would like to look at the metrics of the correlation between multiple variables. It's called correlation metrics. It really helps you kind of look at the comparative correlation between all of the variables, one against another. So you can run that script. You can actually run that command to take a look at the scatter plot metrics of all of your variables, and that will really help. And that's called pair plot or scatter plot. And one of the ways you can do this is to actually do it through the Seaborn module. So SNS, and then pair plot, and then put the name of the data set. So what's going to do, it's going to take a while because it's going through all of these variables, which is almost 30 something variables, and it's actually running one against each other, and it gives you a metrics rundown of your variables in terms of scatter plots. And you can look at the trend and see if there is any correlation between them. So let's see. All right. I think I'm supposed to do. I'm supposed to run a. Yeah, I think I'm supposed to run a plot show, which is already here without me even having done that. But there you go. Uh, I think it's a good practice to do the plt.show method to be able to see the graph. But I would like to see if I can take a look at this on a different tab, a different GUI. So I'll say open image and new tab, and let's see. Again, it's going to be a bit slow because of the volume of the data on this specific data set. There you go. So as I said, this is a matrix scatter plot for correlation between variables. As you can see, we have the breakdown of variables here on the vertical line and on the horizontal line. So as you can see, the variable that I'm interested in is going to be the two independent variables that I'm interested in is the GDP in millions, and that's one of the independent variables. The second independent variable that I'm interested in is the population, and it's going to be uh, yes, it's going to be the GDP is one of the independent variables. The second will be the population in millions. Uh, in thousands per kilometer, and then our my dependent variable will be the emission in millions. So uh, let's the scatter plot metric is one of the ways that you can look at actual the scatter of the, two variables. Another way is to actually look at the correlation coefficient of all of your variables. And so the way you can do that is to run this command right here. And as you can see, as I said earlier, I'm going to be looking at the CO2 emission estimates per million tons per capita will be my dependent variable, and my two independent variables will be one of them will be the one second, I will move to the right. Yeah, um, one of them will be the GDP. Current US dollar, GDP per capita in US dollars. And the next one will be population density. Uh, one second, it's going to be one of these because I saw a higher correlation coefficient between them. Yes, it's going to be, yes. So this will be my first independent variable, which is again the GDP uh, uh, million in million in U.S. currency, and then the second one will be this one right here. Again, the way I'm determining these variables is through looking at the correlation coefficient scores. So both of these have higher, you know, not highly significantly higher, but higher correlation coefficient scores. That tells me that there is correlationship between these variables. So the next one will be at population in thousands. So um, I'll have two IVs and I'll have one DV. So let's get to work. And the way I'm going to do this is I'm going to create IVs and DV, or designate IVs and DV. So designate the independent variable and dependent variable. So what I'm going to do, I'm going to start with X, which will be my independent variable. And I'm going to say data, and then I'm going to put parentheses. Again, the first one will be GDP in million. All right, and then the second one will be population density in thousand. So our population thousands. All right. So we just designated our x, or our independent variable, which is again combined of two separate variables. And then we're going to designate our y, or dependent variable. Same thing. We're going to add the name of our dependent variable, which is going to be this variable right here. All right, and let's go ahead and run this. Let's hope it won't run into any bugs. There you go. So if you want to test it, you can see that we have two variables for x, and we have one variable for y. So both of our variables are now created. So the length is 229, the data type is integer. Same thing with this one. 229 multiplied by two columns. All right, so now that we have designated our IVs and DVs, now we're going to run our test. So I'm going to say run the multiple regression. Oh, I made a mistake with regression. So I'm going to say x equals sm. So remember, it's almost similar as running a simple linear regression. And so we're going to say add. You're going to put the name of your independent variable, and then you're going to say results equals to sm.ols, sm.ols, and then put y and xy, then dot fit results dot summary. So let's run this. All right, we have run into a problem. I think with the stats model, I think I missed the ah, I missed the API. So it activated the module, but not the extensions that comes with the module. So let's see if this can solve the problem. Ah, there you go. Uh, Sorry, each time I click on one of these code blocks, I have to, it's just my habit to, because I've used CLI and base commands and, also SQL, and so I've gotten used to selecting the script that I would like to run. So each time you see me selecting and running it, that's just kind of a muscle memory thing. So, all right, so now we have our result. So let's look at the result here now. We have a variety of information that we can now use. Well, we're going to start with the first thing first. Our dependent variable is CO2 emissions estimates, million tons per capita. Okay, very good. Oh, so our R square is actually very high. So R square, again, R squared coefficient actually tells us how much of the dependent uh, 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 variable can be actually explained by the independent variable. So how much of what we have on the dependent predictions can actually be explained by the explanatory variable, by the independent variable. So whatever we have here as a result of prediction actually comes from 77.9% of explanation that the independent variable gives you. That's what's pretty much telling you. So our adjusted R square is pretty much R square is more like high level R squared coefficient. Adjusted R squared coefficient is actually takes into consideration when you have multiple variables. So in this case, we see a slight decrease in the difference between R square and adjusted R square, which tells us that both of the variables are actually highly correlated and statistically significant. That can be relied upon for this specific model. Uh, the method is least squares, and least squares I don't want to confuse you guys again, because the purpose of this video is to walk you through how to run the model in Python. But the squares, the sum of squares, the residuals, the SCCs, these are more like the statistical minutia that's behind what we see here as a result. So if you were to perform a simple linear regression or multiple linear regression on a piece of paper, then you will see, and then you will be familiarized, with sum of squares, sum of differences, between variables or within the groups. Those are the sort of things. Even when you do statistical test for difference of means, then you would also see the same type of concepts in those as well. So don't get hung up too much on this. Just explaining what sort of method in the OLS model is used for the specific analysis. F statistics is just like we have T distribution, we have Z distribution, we have F distribution. So F statistics is pretty much telling is the test that F statistic is more like used for to is used to test difference of variances in multiple variables. So, for example, if you do a t-test for a difference of means, and if you're using two variables, but if you're using multiple variables, and if you're looking at, if you want to see how much those variables, those betas actually differ, or then you use F statistics. In this particular context, F statistics is testing if there is any difference between. Sorry, remember this from the simple linear regression is actually testing if the difference between the betas here in this equation is zero, then this F statistics, the p-value for this F statistic will be very high. It will be like 90 or 95, not 0.95, like 95. But the fact that we have a F statistic that's below 0.0001, as you can see the scientific notation here, then we're convinced that we can reject the null hypothesis. That the null hypothesis says that the all of these betas, or like all of these components of the equation, or the multiple linear regression, the slopes and the constant, the difference between them is zero, meaning there's nothing significant about these variables for us to be really excited about to use them for statistics. So that's what's pretty much telling you that we can reject the null that says they are equal, there's no difference. But no, we actually, with this p-value, we say no, we can reject the null and actually claim that that the betas are actually different. And it's not only it's different, but it's also statistically tested, statistically validated different. So the time and the likelihood don't the number of observations. Some of these are super intuitive, so let's just not worry about them. The degree of freedom model, since it's a sample, so it's n minus 1. So since we have three degrees of columns or variables, the 3 minus 1, that gives us a 2 degree of freedom. So that's what it is. Degree of freedom for the residuals and the number of observations. Residuals, again, it's kind of tied up with the whole concept of sum of squares and differences, and the regression line, the best fit line, that stuff. It's really not right to talk about it at this point in time. I'm just going to briefly talk about this table is where majority of our information that can help us predict for the dependent variable comes from. So first thing first, let's look at this is the equation or formula for the multiple linear regression, which is this one right here. And as you can see, unlike the univariate or one independent variable simple linear regression, we actually have multiple independent variables, and that can actually go to infinity to say plus b3. Oh, sorry, I always have a problem with this. B3, beta 3, x2, and then beta 4 times independent variable 4, some like that. So the idea here is to use the constant, and then use the beta 1 or beta 2 that our model produced to actually predict for the dependent variable. So let's review the statistical indicators here that come with the predictions here, right? So I would like to start with the confidence intervals. So each time that you deploy analysis, you get a parameter or a confidence interval band between two intervals that actually tells you where your statistic would be at a certain level of confidence. So this coefficient would range from minus 385 to 875 with a confidence interval of 97.5. So, in other words, it goes from 25% to 97.5% between these two intervals. So you can be sure that your slope coefficient falls between these two numbers. And same thing with the two with the two independent variables here. Same thing. Their coefficient is 0.0044, but again it was with the CI of 0.025. it goes from uh, it goes from 0.04 all the way to 0.05. So that's the CI interval between them. And same thing with the other independent variable. So the p-value is actually also, although the overall significance of the test is below 0.01, which is the threshold for social science uh, hypothesis testing. But as you can see, in our case, the p-value for the constant is actually 0.445, which tells us that although the independent variables or although the test is significant and there is a difference between the IVs, but when it comes to the actual slope, it fails our test. It tells us that it's not statistically significant. And this is based on a t-test. It tells us that it's not different, from, with assurance from t-test significance. And as you can see, the standard error is also high. And standard error is the type of statistic that's used to actually do a lot of things. It's very difficult to explain what standard error does, but it measures how much error exists between each of your data points within a distribution, or difference in error. One of the feeding ingredients to your confidence intervals is actually standard errors, where you multiply your standard error um, with the confidence, with the margin of error, and then based on that, you designate the confidence intervals, lower and upper boundaries. So uh, that's what it is. And then again, same thing with these other two. Then the IVs actually are doing well. They are statistically significant with a p-value below 0.000, maybe to the infinity. We don't know. We only get to up to the third decimal. So with t statistics of 17.216, and also this is where the CI, this is where the range, the interval looks like between these two CIs. As you can see, it's not highly different, just as the constant. As you can see, the constant goes from minus 385 all the way to 875. That's a difference almost 1,000. But in our case of these two IVs, the difference is very, very slight. That tells us this slight difference between the lower CI boundary and the upper CI boundary, and also the very low standard error, tells us that these two IVs are actually good explanatory factors or variables in predicting the dependent variable. All right, so let me go back to the PBrush and get a calculator, and let me see if I can also uh, open this page. I need to put 244.80, maybe 81. I'm going to round it up to the second decimal. 244.81. This is going to be my intercept, 244.81, right? And then the GDP IV would be 0.0044, 0.0044, all right, 0.0044. I'm just going to simply call it GDP. And then the population IV will be 0.025. I will run it out because it's only one, so 0.025. 0.025, yeah. 25. Maybe I should just put one since I kept the fourth decimal here. So 0.025. All right, so the way it works is that, once you have uh, the uh, the slope coefficients designated, then you can just need to plug in those numbers into the equation, and that will spit out the dependent variable value for you. So let's hypothetically come up with a number for the GDP and I think the GDP goes from the minimum for the GDP is let's see, I wanna uh, yes, so um, yeah, GDP. So that's why it's good to do descriptive statistics, so you can look at the description of what your data look like. Now that we can see here, the GDP that we're looking at is this one, GDP per capita. I think it's that one. Let me just make sure it's. Oops, apologize. Where did it go? Yeah, yeah. So it's going to be GDP the million current US dollar. Okay, GDP. Okay, so will be this one. So it goes from 2.29, so it's below zero, to maximum of 1.8. So all right, so let's say I would like to use a GDP of, well, let's say, uh, product million US current. All right, so let's say if I ask population towns. All right, let's just hypothetically, let's not worry about the actual data. Let's just hypothetically say that a country has a GDP of, let's say, 1,000. Uh, well, since the independent variable for GDP is in millions, so if I put 1,000, then we're talking about 1,000 million, which is 1 billion. So if a country has a 1,000, 1 billion USD in USD currency for the gross domestic product, and then if they have a population, okay, the population we need to take a look at really quickly, population in thousands. So population in thousands, uh, let's say, uh, let's say 30,000 population, which is not very practical, let's say. And then we multiply these two, and then we're going to say we're going to add that with, oh, no, I made a mistake. So the way it works is $1 billion GDP, or $1,000 million GDP, which is $1 billion GDP, times the slope coefficient, which is 0.0044. All right, very good. So that's 4.4 now. That will be 4.4. So let's just remember that. I think it's better to just use the basic calculator. I could plug this into Excel or even R, or even Python, but I think I'm just doing it here. It's more manual, more uh, easy to understand. And so the second will be the population we said, uh, let's say 100,000 maybe, 100,000 population. So remember, 1 billion GDP and 100,000 population. That times the slope coefficient of 0.0251. That would give us 2,510. All right, so what we're going to do is we're going to add all of these, the slope coefficients and the constant, or the y-intercept. So let's go ahead and add them all. That will be 2,510 plus 4.4 plus 244.81. There you go. So we are going to have a dependent variable. We're going to have a predicted uh, carbon emission estimates of uh, of uh, of 2,759. So this is measured in millions. So we're going to with $1 billion in US dollar in GDP and 100,000 population, a country is is statistically significant to statistically significant predicted with statistical significance to have a carbon emission estimate of 2,759 tons uh, uh, of CO2 emission million per capita. So 2,759.21 million CO2 per capita. So again, how much this whole hypothetical number plugging I did is valid or accurate. I don't know, but again, the whole idea here is for you to understand what a multiple linear regression are and what are the building blocks, and then how you can actually use Python to write scripts to get prediction using multiple regression analysis. Uh, this is it, I guess. I covered pretty much everything. Uh, there are some components that actually go hand in hand with linear regressions that needs to be understood that are important. That they're not core, but they are more like the building blocks. So I will try to cover those in my videos of advanced statistics. So thank you so much for your time and have a great day.